Hello, welcome to Fundamentals of Acoustics. Today is the second day of the 11th week of this course, and what we plan to do today and maybe tomorrow as well is a detailed discussion on microphones, their different types, their different applications, and how do we go around specifying a microphone. So, the theme of the discussion is microphones. And we can classify microphones in several ways. So, today we will classify these microphones in two ways. So, the first way is classification according to their working principle. So, in terms of working principle, there are several types of microphones. So, one category is resistive microphones. The second category, and this second category comes in different names. So, they are called capacitive microphones. Sometimes they are also called condenser microphones, and then sometimes they are also called electrostatic microphones. Okay. So, this is like one set of names. Then we have piezoelectric microphones. Then we can have inductive microphones. Then we can have microphones based on laser, and there is no space here, but another category is fiber optic microphones. Okay. Most of the times when we take measurements, we use either this category of microphones or piezoelectric microphones for doing engineering measurements. You can learn about these other categories: resistive, inductive, laser, fiber optic from references on from the net. But what we are going to discuss somewhat in detail is how these microphones work and how are they specified. So, this capacitive microphone works on the principle of sensing capacitance between two plates. So, what happens? So, in the capacitive microphone, essentially what you have is are two plates, and they are separated by some distance, let us say d0. Then the capacitance between initial capacitance between these two plates is what? Area of the plates times permittivity constant divided by d0. Okay, this is a standard formula. And so let us say these. So, these are the two plates, and I put a charge on these two plates by connecting them to a battery. So, let us say I apply a voltage V. So, this is essentially these two plates act as a capacitor, and when this capacitor is when I apply a voltage across it, then there is a charge which gets developed across these two plates, and the value of this charge is Q. And what is this Q? Q is equal to C times V, okay, capacitance times voltage. So, let us say that initially the charge is Q naught, and that equals A epsilon over D naught times V. Okay. Now, when some sound wave hits this plate. So so one plate is fixed, the other plate is flexible. It is like a diaphragm. It is a diaphragm. So when sound wave hits this other plate which has a diaphragm, it moves back and forth based on the pressure. So this d naught is the initial distance. This changes. Okay. So because of this, there is q naught plus some additional charge. Let us call this qt. This is there, and that is because of d naught plus change in the distance between these two plates. So let us call that dt, and this change is very small compared to d naught. Okay, it is very small compared to d naught times v. So qt, and because this change is very small, so is qt. Q is also very small. So this is equal to A epsilon V one over d naught plus dt minus 1 over d naught. Okay, and this equals A epsilon V divided by d naught 1 over 1 plus d. So now I am just not going to write dt, this d over dt d naught minus 1. Okay. So qt equals A epsilon V over d naught, and d over d naught is a very small number. D over d naught is a very small number. So I can take its approximation. So it is 1 minus d over d naught minus 1. Okay. So this entire term, if I take its binomial expansion and only consider the first term, I get this thing. So this becomes A epsilon over d naught V times d over d naught. Okay. And this d is a function of time, it is actually, and of course there is a negative sign there. Okay. So the point is that if I can measure this change in q, so what is q? Q is the change in charge. If I can measure this change in charge, then I can relate that change in charge to d, and this d then can be finally related to the pressure, because if I have double the pressure, then d will be double, and so on and so forth. Okay. So based on that, by sensing q, I can measure dt, and from that I can measure pt. Okay, I can measure pt. So essentially what I am doing is I use some electronic equipment to measure the charge across these two plates, and by measuring that charge I am able to measure pressure across the capacitor. I am able to measure pressure fluctuation in front of the plate. So this is how these condenser microphones work. In piezoelectrics, what happens is that you have a piezoelectric crystal and you apply some initial voltage across the piezoelectric crystals, so they are a little bit compressed because of that, and then when some pressure hits the piezoelectric crystal, the working principle is that when you press a piezoelectric crystal or expand it, there is some additional voltage generated. So that change in voltage is sensed, and with that change in voltage you interpret that in terms of pressure. So this is how these two devices work, but in both of these two devices what you want is a voltage source here in case of capacitive sensors, or in piezoelectric sensors also you need some excitation voltage. Okay. So, now you can provide this excitation voltage in two ways. Either you have a power supply, an explicit power supply which excites, which provides this excitation voltage. So, in this power supply there may be two sets of cables. One set of cable is there to provide this excitation voltage and the other cable is there to sense the signal. But now there are some special microphones, and these microphones are known as IEPE microphones. Okay. IEPE is an industry standard protocol, and in these microphones what you do is you have just one conductor, okay, and of course there is a ground. So, there are two conductors and these two are connected to the microphone. Now, there may be a preamp between the microphone and the conductor. So, this is your ground, okay, and through this conductor, which is the live wire, which is so this cable I have just drawn it in a schematic way, but in reality a lot of times this cable is a BNC cable. So, in the center there is a copper conductor and outside there is a ground. So, through this conductor the signal travels in this direction in terms of voltage, okay. So, this is the voltage which we want to sense, and then you excite the system, which could be a capacitive sensor or a piezoelectric sensor, by putting in some supply current. And this is typically in between 2 to 20 milliamperes. This supply current for IEPE microphones is provided by the ADC itself. So, sometimes you can buy ADCs which not only sense the signal, but they also supply the current to the sensor. So, if that is the case, then you do not necessarily need this thing, right. You do not necessarily need this thing, you can directly connect this to this. So, your overall system becomes simpler. So, a lot of times, so if you have an A to D converter which can provide the supply current in this 2 to 20 milliamperes, and if you have a sensor which is IEPE type, then you do not need this power supply, you can get rid of the power supply. Your cabling is also simpler, because here in the conventional way you need 7 different cables, but here you just need one single BNC cable to connect it. So, this has become more popular, these IEP type of microphones, but it depends what kind of microphones meet your needs, and if amongst those IEP type of microphone is there and you also have an ADC which can provide the supply current, then that will make your system simpler. So, this is something about microphones. The other thing I want to talk about microphones is their sensitivity. Sensitivity of mics. Okay. So, first we will write the expression for sensitivity and then we will discuss it. So, we designate the sensitivity of a microphone as LS, okay, and in its units are decibels. So, sensitivity of a microphone in decibels is defined as 20 log of 10 Y divided by Y ref. So, what is Y? Y, it corresponds to volts produced by mic when it is exposed to 1 Pascal of pressure. Okay. So, if I expose a microphone to 1 Pascal of pressure and it say produces 2 volts, then Y will be 2. Then there is a reference value of Y, and what does this mean? Y ref corresponds to some imaginary mic, some mic, and we will call it some standard mic. Some standard mic which produces one volts when exposed to 1 Pascal of pressure. Okay. This is one value of Y ref, but there are in the industry there are two reference situations. So this is case A. So there could be one type of a standard mic which produces 1 volt when it is exposed to 1 Pascal pressure, but then there could be case B where Y ref is equal to another standard mic. So there are two different standards we are using. Another standard mic which produces 1 volt when exposed to 1 microbar. 1 microbar. And what is 1 microbar? So 1 bar is what? How many pascals? 10 to the power of 5 pascals is 1 bar, and 1 microbar is 10 to the power of minus 6. So that is equal to 0.1 pascals of pressure. Okay. So whenever some supplier or some vendor gives us the sensitivity of the mic, he will say, oh, sensitivity is in decibels. Let's say he says sensitivity is minus 20 decibels. But then the immediate question is that what is your reference? Is this reference of type A or is it of type B? So this is important to know. So we will just do 2 examples so that we become clearer on this thing. So example, let's say that there is a mic has a sensitivity, and sensitivity is designated as LS, has LS in decibels of minus 26 dB. Okay. And then we are saying that reference is equal to 1 volt per Pascal. So in that case it is of type A. So the question is, if pressure is 110 decibels, what is the voltage pressure is sound pressure level is 110 decibels. So this is SPL. So if pressure is 110 decibels, then what is the voltage produced by mic? Okay. So every time when we are so the first thing we have to compute is how many volts is produced by the mic when it is exposed to 1 Pascal. That is, the first step is we have to find this value of y. Okay. So, we will do this. So, Ls is equal to 20 log of 10 y by y ref. So, this gives us, what is Ls? Minus 26 equals 20 log of 10 y, and what is y ref? 1. Huh? So, this gives us y equals 10 to the power of minus 26 divided by 20, that is equal to 0.0501, and this is what? Volts per Pascal. Why is it Pascal? It is not microbar, it is Pascal because our reference is 1 Pascal, because it is of type A. So, if I expose it to 1 Pascal of pressure, it will generate 0.05 volts. Okay. Now, we want to see how many Pascals 110 decibels correspond to. So, dB, sound pressure level, dB. So, this is 110 equals 20 log 10 P RMS by P ref. And what is P ref? 20 times 10 to the power of minus 6 Pascals. So, P RMS equals 20 times 10 to the power of minus 6 times 10 to the power of 110 by 20. This is okay. Understood? So, if you do the math, this comes to 6.324 Pascals, and this is the RMS value. So, volts produced by mic at 110 dB SPL is equal to what? How many volts? It is 6.324 times 0.0501, and that comes to 0.317 volts. Is this peak volt or RMS volt? This is RMS volt. If you have to find peak volt, you have to find the ratio of the peak and the RMS. Okay. So, this is one example, and in this example what we have done is we have computed volts produced by this mic, which has a 26 decibel sensitivity if the standard mic is producing 1 volt per Pascal. In the next class, we will start our lecture by discussing the other type of mic and see that it produces a different number of volts. So, that concludes our discussion for today, and I look forward to seeing you tomorrow.